Hello everyone, this is codingpros.in, and in this video we're going to discuss an optimized approach to the same problem, toSum, which is given an array of integer nums and a target value. Return indices of two numbers such that they add up to the target. So in the previous video we discussed a brute force approach to this problem. In this case, in this video we're going to approach a more optimized solution. So yeah, the problem is pretty clear. Given an array 2, 7, 11, 15 and a target value which is 9, we have to find two numbers such that they add up to 9, and we have to return the indices of those. So in this case 2 and 7 add up to 9, and the indexes of those are 0, 1, right? So we have to return 0 and 1. So okay, we have discussed the brute force approach. If you haven't watched it, you can check my previous video. And let's discuss the hash table approach here. So one way to reduce the lookup time from O of n. So what do we need to optimize here? We need to fix a number, and if we can optimize the lookup time, if we can remove the second for loop and instead change the lookup time from O of n to O of 1, we will achieve an O of n time complexity. Cool. So how are we going to do this? We know that a very common way to reduce the lookup time from O of n to O of 1 is using a hash map or a hash table. Okay, so this approach is a two-pass hash table approach, and what we are basically going to do is, while going over the array 2, 7, 11, 15, we are also going to store the indexes. 7 has 1, 11 has the index 2, and 15 has the index 3. So you're going to store the indexes in a hash map. Okay, now once we have this hash map created, what we can do is we can fix an element. Suppose we fix 2, and we can find whether my hash map contains the number target minus 2. Cool enough. So in this case we see that yes, the hash map has the number target minus 2, target is 9, which is 7. So in this case we can just return 2 and the index here. The index here is 1. We can return the first index 0 and the second index 1. So yeah, this is the most basic approach. So we are going to iterate over all the elements, and we are going to put them in hash map. And after putting them in hash map, we are going to go over the elements again. We're going to go over the elements again and see that for each element whether the complement of those exist in the hash map or not. If the complement does not exist in the hash map, that means there is no such pair which would add to target, and we would move to the next element. Cool. This would give us a O of n time complexity and O of n space complexity because we are using a hash map. So let's go ahead and try to code this so that you understand a little better. And if you don't understand it yet, don't worry about it. Once you see the code, you can understand it better. Okay, so sorry about that. I'm just going to initialize a map. I'm going to say, okay, so this is my hash map, and I'm going to go over each element in the array. And I'm going to do nothing but put them in the hash map. So my key of the hash map would be the element itself, which is nums of I, and my value would be the index, which is I. Okay, once we have this hash table created, so at this point we have this part done. This part is created. Okay, now on to the next part. So we are going to go over each element of the array, and we are going to check whether the complement of that element exists in the map or not. Cool. So I'm going to say I equal to 0, I is then nums dot length I plus plus. I'm going to say, hey, my complement is nothing but target minus nums of I, right? This is going to be my complement, and I'm going to check if my map so if my map contains this complement, and we're also given that you may assume that each input would have exactly one solution, and you may not use the same element twice, which means that I cannot use the same element twice and the elements cannot be at the same index. So I'm also going to check if map dot get of complement. So get function only returns the value for that particular key in the hash map. This should not be equal to the same index, which is I. Okay, cool. If this is true, I'm going to return a new integer, which is my index I and my index of the complement. So index of the complement is nothing but map dot get of complement, and we will be done with this. Okay, and if we do not get an element like that, we are just going to return null. But again, so the null block will never be reached because this is given that the solution contains this problem contains exactly one solution, so each input would have exactly one solution. So yeah, let's try to run this. Okay, so you can see it's finished, and my expected output is 0, 1 and my answer is 0, 1. Let's try to submit this answer. Okay, so you can see that it has been accepted pretty quickly, because yeah, it takes a less time because it's O of n, and the space is also O of n. So the time complexity for this would be O of n, and the space complexity for this would be O of n. But there is a small catch. Okay, in case of the time complexity, we traverse the list containing n elements exactly twice, right? And since the hash table reduces the lookup time from O of n to O of 1, the time complexity is O of n. Okay, so don't be confused about I'm using two for loops, why is it not O of n squared? So it would be O of n square if the for loops are nested, but these are two separate for loops and we're only going over the elements once. Okay, and the space complexity would be the number of items stored in the hash map, which is n elements, and hence the space is O of n. Okay, so the catch here is to reduce the lookup time from O of n to O of 1 by trading space for speed. A hash table is built exactly for this purpose, and it supports fast lookup in near constant time. I say near because if a collision occurred, a lookup could degenerate to O of n time. Okay, but lookup in hash table should be amortized O of 1 time. Now, what is amortized O of 1 time? This simply means that most of the times it's O of 1, the lookup time in hash table. Okay, and as long as the hash function was chosen carefully, it will be O of 1. So I'm considering the case that there are very little collisions within the hash map, and because of the few collisions, the lookup time is O of 1. So if there are a lot of numbers and if there are a lot of collisions, the lookup time would again degenerate to O of n, and this solution would have a time complexity of O of n squared. But in most cases, it would be O of n, amortized O of n, the time complexity, because the lookup time is O of 1. If you have any questions regarding amortized space complexity or anything at all, leave the comments and I'll get back to you on that. And I'll try to cover more about collisions in hash map and amortized space time complexity in upcoming videos. But this video is more directed towards the solution to this problem. So I hope this is clear. If you have any questions, let me know. And thank you for watching. Bye bye. Have a good day.